então iniciar o seminário de hoje, it's a pleasure to have here Professor Yves Galerne. Professor Yves Galerne, I know him when I was in Alcep 25 years ago, probably 30. And Professor Galerne had his master thesis, in our words, and PhD thesis with Pierre-Gilles Degé, Nobel laureate. And he was in Alcep for many years, a lab there. And after that, he became a professor of physics at the University of Strasbourg. Actually, his diretor adjunto dessa escola Institut de Physique de Chimie de Matériaux de Strasbourg. He has very important contributions in the field of electrolysis, and our friend of us, it's a real pleasure to have you here and accepted our invitation. Thank you very much.
Thank you very much, Antonio, for the very nice presentation, and also that you have invited me to visit your lab here, and to give me the opportunity of present this talk, which covers research I'm doing for about now 10 years. Yes, the title seems to be, I would say, surprising, because you see here I intend to make microwires, and it's not clear at all, I think, what our leaf crystals are doing here. So I have a subtitle to express this surprise, maybe. I've been working with 3 people for this subject. Now I work with Rakia Maga, who is going to stay with me and continue this problem. Previously, there was Jean-Baptiste Fleury, he's now in Germany for postdoc. And also, before that, there was a Portuguese student who began this study. He's now in position, full position in Switzerland. Okay, my talk will have several parts. I begin with an introductory part about microwires that maybe you know. It is just to introduce the subject. After that, I will speak about the properties, very interesting properties of nematic crystals that I use to make these wires. If I go too fast, please stop and ask me to detail maybe things which are evident for me but not for you. Also after the talk, I'm free for discussions if you want to go further. Then I will detail the process which I use to make these wires, and there are several steps. The first step uses discriminations, which are defects that exist in the crystals. These defects, then, I use them as template to make the wires. And there are several steps at this stage. First, we use particles that are attracted toward the distillation line, and they build what I call a micro-necklace. We'll see in a moment. After that, the particles are trapped on the distillation line. I will discuss this problem, and then we stuck them by an electropolymerization process. At this stage, we have materialized the distillation, and it becomes a wire. And to prove this, I produce some tests at this moment. Okay, so let us come to the first point. about the micro and nano wires that are already available. Here, for instance, you see silver nanowires, which are produced by a chemical reaction. I do not remember exactly the way, but it's very simple. It is inside ethyl and glycol, so it's a reaction. And you see that the rods you get are very, very thin. Here, the diameter is about 50 nanometers, and the length is more than 2 micrometers. But these rods, you see, are at random. They are at 3 dimensions, and they are not connected to electrodes. Anyway, they have applications, for instance, with light. I will not detail these, but they may be used non-connected. But of course, if you are able to connect them, then you open the door to more applications. So the question is, how to connect them? How can we do to connect them? And in fact, there is a possibility which is used already, and I'll show you in a moment, consists in making the connection in 2 dimensions, but then you use the 3rd dimension to operate the connection. Here, the rod is, for instance, there, and you push it with an AFM, an atomic force microscope, at the right place in contact with the electrodes. It's a way that works, and in this manner you can get devices. And here I give you some examples. The rod is there, you see, and the electrodes are obtained by metal evaporation or electron beam lithography. And in this case, the rod is made of is a phosphor of indium, and it's a photodetector. And here you have, of course, built a nano photodetector. Other possibilities are to go in the other way. You produce the rods parallel to the same direction, and they are obtained by and they are synthesized directly against steps on a graphite crystal, and you evaporate the electrode in a second step, and then you get, for instance, in this case, an hydrogen detector. Now, what I aim to do is a connection in 3 dimensions. So, suppose you have two electrodes, one on this plate and another one on a second plate like this, but it is in space, and you want to connect the 2 electrodes by a rod like this. Of course, you cannot go there with any mean, by any mean. Even an AFM is able to do this. Yes, this could be very useful for maybe very important applications. You all know about the Moore's law, which says that with time you can reduce the size of the component of electronics, for instance, transistors and capacitors, etc., are narrower and narrower in the large-scale integrated circuits. But clearly, there is a wall that can be overcome if the size of the atoms. And in fact, the wall is much before this, because you cannot go really at smaller sizes than a few nanometers. We have time before this frontier, this barrier. We have time yet, because now the typical size of the large-scale integrated circuits, the size which is used is about 20 nanometers. But it's coming down every day, and we will have this limit. And so it's maybe the moment to think about going in the 3rd dimension. with the process I propose, you shall see that it's possible not only to make one connection, but a lot of them at the same moment, and also not only on the stack of two circuits, but a lot of them at the same moment. Remember that our brain is connected in 3 dimensions. So what I propose is with this possible application. Yes, in the method I use, I put a little pistol first in between the two parts to be connected. In the following of my talk, this direction will be called the Z direction, and the in-plane axis will be X and Y. You can say, oh, but it's possible already to make Y's which are perpendicular. It's impossible to grow Y's perpendicular to the substrate. They can go they can start just from an electrode. So you can say, oh, this connection is already realized. In fact, you can immediately imagine that if you have one connection, you cannot connect the second one. It's impossible, nobody knows. So you have several examples. Yes, I just show you these possibilities, where only one connection is done, and the other one is not possible to get it. So it's difficult. In fact, it's more than difficult, it's not possible. So now let us come to the process I propose. It uses the properties of liquid crystals. So now I will present you some characteristical properties that I use here. And the first one, I must recall, I suppose you know this, that in nematic liquid crystal you have an orientational order. I mean that the molecules are elongated like this, and in the nematic phase, they are like in this drawing. They are not strictly parallel to one another, but statistically they are. And they are parallel to a common direction, which is called the director. This director is the unit vector, which is used to mark, to know what is the common orientation of the nematic. Of course, when you have an order in a system, you can play and you can deform it. And we call this distortions. And distortion of the director may be of several kinds. Here you have a band distortion. You can see that the director is marked by the red arrows, and the blue lines are the field lines of the director. You can make also splay deformation, is like this. Here, in all the problem I am talking on, we consider always that there is no distortion along the Z direction. I mean, it is roughly uniform. So, because of this, the distortion will be only of bend and splay kind. If we had three-dimensional distortions, we would have the twist distortion also. When you make this distortion, you give some energy to the system. This is the elastic energy here. And this is important for the following. But before I go to this point, I must also make a remark. That is the director N. You see, in fact, maybe in the other direction, just because the choice of the direction of N is arbitrary. The director may be reversed. N is equivalent to minus N. This remark will be used in the following of my talk. So, the distortions have consequences. When you put, for instance, an object, here it's a particle inside the liquid crystal, you have a preferred anchoring direction of the molecule around it. In the case here, the molecules are perpendicular, and so you see that this makes a distortion of the diatom all around. When you put two of them, of course, you have this, and you have spray here, distortion, but you can see that the field lines have to connect, and all this part is distorted too. Of course, because of this distortion, you have an elastic energy which is produced by the presence of the two particles. This elastic energy in excess when you push the two particles close to one another is at the origin of the force. Just because if you take the derivative of this potential here, you have a force, and this force is called the nematic force, and it has been shown by Lubensky about 10 years ago. And because of this, you have forces which act on the particle. And it is interesting because we lose this force. The spray distortion is represented by a vector, and the vector is n divergence n. You can see that this vector, it does not change sign when you reverse the sign of n. We say that it is an invariant, and it's necessary just to have a physical signification. Of course, you can use it to write the elastic energy related to the distortion. This is just here, the formula here is just a generalization of the usual elastic energy of a spring. If you pull on a spring, you have the distortion, generally called x, and the energy equals then 1/2 of k, which k is the elastic constant of the spring, times x to the square. Here it's the same thing. The distortion now is just the spray vector to the square, instead of scalar, and ks is the elastic constant. Here you can see that this energy is similar to the electric energy, and you can see that you can make an analogy with the electric field in electrostatic. This analogy will be useful in a moment. The same thing can be done with the bend field, but maybe I'll skip on this. You have to calculate the curl of n. It's perpendicular to the figure, and then B, the B field is directed like this. It is a true vector, and its energy has the same form as for the spray I gave you a moment ago. To have the complete elastic energy, you just have to add up the two contributions and to integrate this energy over all the points in the system. This is not very simple. You may subtract also the self-energy, which is obtained when you have just one particle, and when you subtract the self-energy, you are left with the excess elastic energy, which is the elastic energy due to the interaction, what I called U a moment ago. You see that it is not simple to get U and then to calculate F. And we shall use another method. We shall make multiple expansion, which is valid formally only at large distances, but in fact we see that it works even at very close to the particles. Each term of the expansion is an energy, so it needs to be a scalar, And it needs also to be invariant upon n reversal. I mean, if you change n to minus n. This is called the electric analogy, and has been proposed by Lubelsky more than 10 years ago. Okay, now I go to a second consequence of the distortions. The distortions are at the origin of topological defects. You see here, you have the distortion all around the particle because the director has radial orientation. And if you follow the red path starting here, all around the particle, you can see that during this term, the director makes also one term. So, and in the same direction. This is why it's called a +1 defect. You see? So when you make a turn from here to this along the path, you see that the director rotates by also 2 pi. It makes the turn 2. It's a +1 defect. You can also have this case when the distortion is strong. Yes, I forget in the present case, but I say now that at this place it's a defect just because at this place it is impossible to tell in which direction you have the director. There is no more, it's not possible to give a direction. This is why it is called a defect. And when you make here the same analysis as before for the +1 case, you see that starting here, the director which is up then goes here horizontal and back is down. So this is half a turn for the director when you make a complete turn for the path. So it's a +1/2 defect. We say this defect are called discrimination lines. Here below is another case where when you make the turn, the rotation is a -5 radiant. It's -1/2 turn, so it is -1/2 discrimination line. We can go a little bit deeper in the problem of the discrimination because we need a little bit. Here is a +1/2 discrimination line represented in a different way as before. You see that alpha is the tilt angle of the director is just equal to theta over 2, where theta is the and r are the polar coordinate of the point you are guarding. 1/2 because this is a +1/2 discrimination line. It means that the director rotates at of the quantity which is half the angle theta. This is condensed in this formula. Of course, this formula defines completely the field of the director all around the discrimination line. It's very easy to write a director, and when you have a director, you can calculate the derivative of it. The calculus is simple, but I do not want to enter into the detail. Just see that the divergence of n is of the order of 1/r, and you may just use a dimensional argument to reach to this result. You just see that n is equal to 1. Its modulus is equal to 1, so has no dimension, and you take the derivative, so the dimension of the divergence n is 1/length. So the only one length in the problem is r, the distance to the core of the discrimination line. So you get to this estimation, which is enough for us. And of course, when you have divergence n, you can calculate exactly the splay vector from which we had the energy. Okay, now I think we know enough about the nematic properties of our application. The first step to make the wire is to build up the template. And we will use this inclination as a template for the wire. What we prepare destinations that are connected in three dimensions at the right place, and to join the 2 point P and Q to be connected. And for that, we use surface conditions, appropriate surface conditions on the two surfaces of the substrate where the line will be connected. And to not spend too much time on the techniques of this alignment layer. In our lab, we use a Teflon film. We rub in this way on the plates, and then when you put a crystal on it, you see that you have planar anchoring, and it means that the molecules get parallel to the rubbing direction. To make the destinations, we need conflicting orientations, and we get this by 3 different rubbings on the same plate. But in the first rubbing, all the plate is rubbed along this green arrow. In the second rubbing, we pass only half the plate along this green arrow, and in the third case, we rub again along the half of the plate along this arrow. And so what we get is this. Here we put the liquid crystal on the plate, and you see that the liquid crystal is oriented along the yellow arrows, which correspond to the rubbing directions. So it works. If we do the same for 2 plates that we put in front to one another, we obtain the orientation of the field director in blue as indicated on the figure. Yes, and you see that you have then a destination line, which is a +1/2 destination line, perpendicular to the point P. You do the same on the 2 point P and Q of the 2 plates, and you get the destination line along the red line. You see that the connection is flexible, so it's not straight, that doesn't matter. And also, it's flexible in the sense that you do not need to push P and Q exactly in front to one another. It has to be roughly in front, at the accuracy equivalent to the spacing distance. We work with distances for the moment which are about 150 microns, so we can shift this quantity. It connects without any problems. And here you see photographs of the wire. No, it's not the wire. Here is a destination line for the moment, and with 2 different focusing of the nematic. You see the black line. Here is the destination line. The 2 plates are shifted in order not to be perpendicular, because then you cannot see. I indicate here the way to generalize and to have a lot of connections at the same moment. In the method we use of rubbing Teflon on the plates, you have to make the rubbings along the direction according to the number I indicate. In the first rubbing, you rub all the plates along this red arrow. In the second one, you rub only this part along the green arrow, I say, yes, etc.
What are the dimensions of these domains?
When you use the Teflon technique, the distance is about 1 millimeter. You cannot, it's difficult to get narrower passage it's a technical problem, but there are other ways to make the alignment layer using, for instance, evaporation of oxide, silicium oxide at an oblique incidence. And you can do this with masks. And then you do not need to have the surfaces which are like this, like parallelograms, well aligned one to the other. This is due to the technique of running. But you have all other techniques. Also, another technique consists to use polymer, which is polymerized with UV light, with polarized UV light. This is commercial, and a lot of screens for TVs are produced with this method. Each pixel has a different polymer alignment layer, and it's possible to use also this technique. But I'm not equipped to do this, so I use.
I have to discuss with you.
Yeah. Okay. So in this method, you can make a lot of connection if you need. Now I go to the second step. I use particles which are dispersed in the nematic. I began with big particles, 1 micrometer of radius. Now we work with particles of 120 nanometers. And what happens? They are attracted toward the destination lines just because of the nematic force I presented to you a moment ago. In the presentation, I gave you examples where the force was repulsive, but in this case, it is attractive. Okay. So, what happens? Here is a particle. You see, the anchoring of the molecule is perpendicular to the particle, and so you see that the molecules are radially oriented, the director is radially oriented around the particle. This means that it is a +1 defect. The particle is equivalent to a +1 topological defect. You can see that just close to it here, there is a -1 defect. You can see that here it's the feed lines follow hyperbolic directions, which is a -1 defect. You can see that if you make a path all around like this, you see that the director keep horizontal. So if you make a path like this, the total number of topological defect is 0. So you need a -1. This means that you have a dipole moment, a topological dipole moment, P, and you can see that it is associated with a splay deformation, which corresponds to the blue bars, which in this place you have a splay. So you can see that the defect, the topological dipole moment produces a splay, and this splay naturally will be coupled to the splay field produced by destination lines in the neighboring. So if you have a destination line, you have a connection of P to this splay field. Of course, you have not many ways to make an energy. The energy is scalar. When you have two vectors, moment here is a vector, this field is a vector, you make the scalar product. K is just a constant, an elastic constant, to give you the good value of the energy. This is what I told a moment ago, the multipolar expansion. Here is the first term of the multipolar expansion. Of course, there are higher order multiples, but you can neglect them. This one is the most dominant one. let me come back to the analogy with electrostatics. So a discrimination line is a topological line, contains topological defect, plus one, or plus 1/2 or minus 1/2, depending on the discrimination you have. It's equivalent to a line of electric charge, Q. The discrimination line produced a spray field, and which is, I argued a moment ago, it is of the order of 1 over r, the distance of the particle to the discrimination line, and it is equivalent to this field, equivalent to the electric field which is produced around the electric line. You can calculate using the Gauss theorem. I drop here the factor 2 pi epsilon 0. Okay, and the energy here is this one, or of the order of 1 over r, and here the electric energy, you know, is this minus p scalar E is of the order of 1 over r. So they are analog. And of course, to get the force, you take the derivative, it is 1 over r to the square in both the cases. I go fast on this point. The calculation may be done exactly as soon as you know the expression of the n vector. I gave you a moment ago this value. This is not a difficult calculation, but I draw it. Epsilon corresponds to the index of the discrimination line, depending on which one you want. The force is obtained on taking the derivative, so of the order of 1 over r to the square. When the particle is in the nematic is a liquid.
Slide d'avant. The field is not the field of an electric, a monopole. Because the field of monopole is not on the other side. E is not proportional to 1 of r squared.
Yeah, here I go just back here. Yeah. You see here it's a line. I consider a line of electric charges which is perpendicular, which is along z, and perpendicular here to the plate.
And it's a line charge, not a punctual charge.
No, here it's not a punctual charge. Here the discrimination lines are lines.
Okay.
So I make the analogy of a line of charges, and the Gauss theorem is you take a cylinder,
Okay.
and you calculate the flux of the electric field across the cylinder, and you get the flux of E is equal to Q over epsilon 0. So you can get this. I got just the equation. So yes, and what I was just saying is that the particle is in the nematic, which is a liquid. It's a crystal because you have an order. It makes defects like a crystal, but it's a liquid. This means that if you have a force which pulls the particle, you will have a Stokes force which will be opposed to this force. The acceleration is 0. So if you write the mechanics of this problem, it's very simple. It means that the two forces are equal but of opposite sides. The Stokes force is simple to write. It is this, where r is the radius of the particle, v is its velocity, and eta is the viscosity of the liquid crystal. The viscosity is tabulated, you just have to take it in literature. The velocity of the particle, you can measure it. We take photographs, and we then find the distance, which is the distance of displacement of the particle this time. When you write that the two forces, this one and this one, are equal, you can see that you have a differential equation. You may integrate it it's not very complicated, and you get the trajectories, the theoretical trajectories on the particle. But now I go to the experiments. So I was explaining that we can measure the velocity. So we know this force, which is equal to the force that pulls the particle, and we do this as a function of r, and you see the data, the force against the distance in logarithmic scales. Pay attention that the force is very small. Here the unity is pico-newton, and here it's 10 to the minus 1. So the force is really, really very small. But we measure it, and when this, you see, is a straight line over 1 decade, this means that it's a power law, and the exponent of the power law is very close to 2, which corresponds to what we have theoretically discussed in the theoretical part a moment ago. And now, let us come a little bit more in the details of the experiments. Here, so I say that we take photographs from above. The destination line is perpendicular here at the origin of X and Y. And in color, we have each cross or point corresponds to one photo of a particle that is taken when time is flowing. And we see that for a particle which starts here, the particle goes in this way. You see that it follows the trajectory, the theoretical trajectory. Yes, this is for plus 1/2 destination. The expression of the theoretical tracks is simple, and so it works well. Yes, there is no fitted parameters. Here in this formula, the only one parameter is R0, and when you change this value, you just change the trajectory. There is no fitted parameter. What's important to see also is it is a fluctuation. It is just Brownian fluctuation. And this fluctuation is useful. We can analyze it. We draw here, we can calculate this, and we make an average over the time. And this is only the diffusion law. From this diffusion law, with time tau, we get here the slope here, give you the diffusion constant.
What was the dimension of the particle you were using in this experiment?
Yes, the dimension, we measure it, we know it because we know what we, but we always fear, you know what, when you put particles in a liquid, not only a liquid crystal, you fear that they go and form aggregates. So when you find a point at the microscope, you do not know the size of the object. So you need to measure it, and here we measure D, the diffusion constant, and with this formula we deduce R, because we know K here is a Boltzmann constant, T is the temperature in Kelvin, and alpha is stability. So the only one thing we do not know is R, and since we measure D, we deduce R. So we know that we have no aggregate, we know if we have an aggregate or not. We know the size, just on using the diffusion behavior of the Brownian motion. So this is the diffusion part. After that, it decreases back to 0, just because the particle is not a free diffusion. It's a diffusion, but which is limited to the attraction by the destination line. Because at the end, the the particle will be stuck on the distribution line. So it's not a completely free. The free part is just at short times. After that, it's correlated to the position of the destination line. To be fast, it works similarly. I show you rapidly this the case of -1/2 destination line. You see the trajectories are different, so the equation then is different, but it works similarly. Okay. So in conclusion for this part, you see that the splay field, which is produced by the destination line, in fact is dissymmetric. You see it's symmetric because here is the destination, the splay field is strong here, is 0 there, and is a medium on the lateral positions. And because of this, you have not a complete, you have not a full analogy with electrostatics. It's evident that you have not a full analogy because the trajectories are not straight lines. If you do the experiment in the electrostatic, the trajectories will be straight. I emphasize on this point because on the literature people forget to say this, that it is not a complete analogy. The same thing works also, I look if I have time, not many, so I go very fast to this. It works if you go to planar anchoring, then you have quadrupolar interaction. I do not detail the topological defects are 3 now, and they make 2 opposite splays like this. The energy is a little bit more complicated. It's a derivative of the previous one. So you go here to 1/r to the square. The force is then, you take another derivative, is to the third. And the experiment works very well. Also, you have the measurement of the force here versus r give you an exponent very close to 3. Again, the trajectories are not straight. And okay, so now I go to the next point. I have to discuss that the particles are actually trapped. It is important because when I began this with my Portuguese student, who was a very good student, he failed. Because at that time, I did not use big particles, I used monomers of I don't remember which compound, and the monomers were not trapped on the destination line. So we have to prove that, to argue why these particles are trapped and not monomers. So the situation is this: the particle is there, is attracted. Do we have trapping on the defect line between P and Q? Here, for the last step, I will make voltage between the electrons, but not here. Not for this the tracking of defect on the defect are discussed. They are then called by contrail effect, and they are simply discussed in terms of free energy. You need that the free energy of the system is decreased when the particle goes from the dispersed state to the trapped state. Of course, for this, you need to decrease strongly U and not to increase too much S, because S is increased when the particle is stuck on the line, because on the line the entropy is increased. Let us estimate the gain. Maybe I go fast on this also. The interaction energy of a particle, of liquid crystal particle with the particle, liquid crystal molecule with the particle is the van der Waals type. It is of the order of -kT. The anchoring energy is about 10 times lower. The anchoring energy is just the difference between the van der Waals energy in the perpendicular direction with the van der Waals energy with the parallel direction. And when the particle will be stuck on the line is disordered, so there is no constraint for the anchoring. So the anchoring energy will be decreased, but not so much. We may estimate roughly, it's enough for what we do, about 1 order of magnitude of the anchoring energy. So if you want to calculate the gain of energy when you stuck a particle on the line, you have to take this quantity per molecule and multiply by the number of molecules in contact. It is the area of the particle times to the area of contact of 1 megaparsec molecule. This is not complicated to do. And at the end, you get this potential energy you gain in the operation. Let us now estimate the variation of the entropy. It's the difference of the entropy when the particle is on the line, minus the entropy when it is not. The entropy, you know, is given by this Boltzmann law. It's written on the font of Boltzmann. You know that it's suicide because nobody recognized that it was right with this formula. It is my homage to Boltzmann. And omega is the number of configuration of the corresponding state. It's easy to evaluate as the volume of the accessible state divided by the volume of the particle. And in the case, so for the line, it's the length of the line divided by the diameter of the particle. And in the case of dispersed states, it's the volume. L is the spacing distance, big L. A is the area, typically it's L to the square. So this at the numerator you have L to the third divided by the volume of the particle. I drop the K, the 4 the third to here to just so you can calculate easily delta S, and you gather all the with delta U, and you have the delta F. This has to be negative for the line to be attractive. When you put figures, it's not difficult to find that this is of the order of 10. So you end up with this, and this means that the radius of the particle has to be 3 times the length of the equidistal molecules. And this explains why we failed when we used monomers, which length with diameter was about the same as the length of the particle. Now we work with particles which are 10 times larger than this, so this is why they get stuck. And here is a necklace. It is a line with the particle stuck on it. Here there is a growth of the dendrite. The size of the bar here is very large, about 30 microns. Now we have seen that we reach the last step. We have to stick all the beads, all the particles, and for this we use electropolymerization. It's a chemistry. I'm not a chemist, but I can explain simply. First, we have dissolved a small quantity of pyrrole, which is a conductive polymer, a monomer, with this salt, which is an oxidant. And then what happens? The pyrrole is oxidized by this ion, or also oxidized on the electron. You have both possibilities to give this radical, which spontaneously give the polymer. This polymer is conductive. Here is a sketch of the necklace. The particles are previously surrounded by a very thin layer of polypyrrole, which is this conductive polymer. Suppose you have a break here. This makes, when you put the voltage on the electrodes, you see that you have the delta V here. So these beads here work as microelectrodes. And around this, you will sensitize a little bit of polymer. And what you get is this. This was our first photograph. It's not very nice. Here it's very thin at this place, but you cannot see here at this place. The thread is vertical, so you cannot see it. Here there is a very bad aggregate. Do not worry with this. But the question here, I will try to. Yes. It is the same thing, but with different focusing obtained by my student. The thread is stuck on one plate here, and here also. Here there is a bad thing on the alignment layer. Okay. But things are not so simple, because you have not only electropolymerization, there is also competition with spontaneous polarization on surfaces, but also in the volume, depending on concentration and temperature. And so you risk to end up with a gel. And so what I show you maybe could be something like this ant here, which is embedded in a piece of amber for maybe 1 million of years. We have to make tests to prove that it is not the case. And the test I give you now, first we suppress the nematic force, which attracted all the beads. If you have not polymerized, the particle will be dispersed immediately. And we suppress this just on going on into the isotopic phase. We just have to heat up the sample, and this test does not exclude that you have a bulk polymerization, and the proof is there. Yes. You see the point P is here, and Q is just above there, and you see that the thread is floating like a flag in the air. There are big particles that are that shows that there is a flow. Here, the particle hits the thread, but does not break it. So now I reach to the conclusion. We have shown that we have got micro wiring in 3 dimensions, and it was connected at the right places, and this is due to smart properties of the liquid crystals. I would say some words on liquid crystals. They are able to do things which are not possible by any other known ways. I did not give the figure about the last experiment on the flow. The flow is in fact seen to be very fast. It has in fact, I think, less than 5 micrometers per second. So I was able to evaluate that the thread was able to resist up to 1 nanonewton, which is not a lot. About the electricity, it has to be weakly conductive because it is obtained by electropolymerization. We tried anyway to measure its resistance, but we find 2 megohms, but we cannot be sure that we have leaks on the borders. So I cannot say it is exactly the resistance of the wire. Now it's not finished. the subject is under progress. What we are doing is the downsizing. The thread I showed you a moment was obtained with big particles. Now we have increased the size by a factor of 10. We shall use very soon carbon nanotubes because then we will have not spheres but rod already, which seems to be more appropriate to make threads. And after that, when we obtain a good thread, we will increase its conductivity by electroplating. For this, we shall have to remove all the crystals and to replace it by an appropriate electrolyte. Thank you for your attention.
Very nice. Let's open for questions. Which kind of crystal you use?
Yes.
5CB. So
yes. I use 5CB, which is, I would say, about the same crystal that you have in this screen, and in every application. This molecule is very interesting because these molecules have many qualities. It is a room temperature nematic. You do not have to have control of temperature. It is a very strong molecule which does not degrade so much with time, etc. So we use this molecule. Also, another advantage of 5CB is that you find the data, for instance, of the viscosity, of the elastic constants in the literature.
You think to use homeotropic crystal with delta epsilon, different delta epsilon for this experiment?
In this experiment, we do not use the electric properties of the crystal. We apply electric field. It is just to make the polarization, and the electric field is small, very small. We apply just a few volts across the spacing distance, which is more than 100 micrometers. So the voltage, the electric field is very small. We do not need the dielectric properties of 5CB. We do not use them.
You are using particles with micrometer dimensions.
We used the particle with a radius equal to 1 micrometer first, and now we are working with much smaller particles, which are 10 times smaller. But of course, it's not so easy. You cannot see them easily under the microscope. They tend to aggregate because big particles are easily charged, and they have the same charge, maybe typically 20, 30 electrons on them. When you reduce the size of the particle, the charge decreases. When you get one electron, statistically you have also zero charge, and then they do not repel, and they aggregate. And this is the problem with the small particles. I think we will have also the same problem with the carbon nanotubes.
Well, I understood you want something which conducts electricity between two electrodes. Why don't you put, for example, microspheres of iron?
Of iron?
Yeah, iron.
Yes, it would be possible, but the problem is essentially to get stuck, to stick the particle one another, and here the conductance is obtained we work with glass particles, I forget to say, but we recover them with a thin layer of pyrrole by an independent operation before putting them in the nematic system. So the conductivity is only on pyrrole in our case. But you are right, it would be better that the particles were conducting by themselves.
For example, in magnetorheological fluids, you have magnetic particles the size of microns.
Yeah.
It could be very good because it can attract the dipole moment for the other.
This could be used, tried, I think. I intend to try with carbon nanotube also because carbon nanotube are conductive. But of course, other ways could be
Not interesting. The piezoelectric particles are very small, but the magnetorheological fluids could be
difficult. I see. I agree.
Quando se usa uma partícula magnética, lógica não é maior?
maior. Mas o que ele quer são partículas maiores. As menores são difíceis de trabalhar e ver, ele consegue ver no microscópio. He's asking why we don't use ferrofluids. Because we cannot see the particles itself. We use the micron side of the particles is easier to see.
Professor, I'm having some difficulty, and I would like to ask you, you pass the electrical current between the electrodes through the wire.
To make the electromagnetic polarization, we applied a voltage. I did not detail because I saw that the time was on. In fact, it is an alternative voltage. In order to avoid that the pyrrole goes, you see that the pyrrole is produced via the formation of a radical. Here it is. You see the positive radical. So if you apply a continuous voltage, you see that this polymer will only appear on the negative electron, and we want that it sticks. So we need polymer on the both sides. But your question was
Okay, no. Your objective is to pass, to make an electrical contact between the electrodes. And did you pass a current through it?
We apply a voltage. And,
okay. And then, is it an on contact? Or
at the beginning, it is not, there is a break like this, but at the end, it is stuck. And so at the end, you need to have a contact. It is mechanically stuck. You cannot explain what you see during the flow if it was not stuck. And because the glue which is used is conductive, I think it's a good argument to say that the wire is actually conductive. But as I explained, it's difficult to measure the real resistance of the wire. What I measure is 2 megaohm, but I cannot discard the possibility of a shortcut by the borders.
How did you measure this resistance? You measure with continuous voltage? Or
with a continuous voltage.
Maybe it's different if you use different frequency regions, or even electrical pulse, charge electrical pulse. I don't know.
Yeah. Of course, when you use an alternative voltage, you do not need to have a contact, because then you have a capacitive junction and current. But in continuous current, it is more difficult. So
was thinking some biological connections have electrical pulses. I don't know, brain, something like that.
When you use alternative currents, there are two. There are a real lineament of with crystal too, or not?
There are
Real lineaments of crystal.
real not in fact, because I have only a few volts, and
This one
the thickness is large. I say 150 microns, and so this means that the electric field is small, and so then no realignment. Just to tell you, in this screen, the spacing distance is only 6 micrometers, and the voltage is probably 10 volts. So the field is really huge. I would say 100 times larger than mine I use here. 100 times. So we do not have a realignment. You are right, it's a good question, because we must not make perturbations on the electric crystal alignment, otherwise the line will be distorted, and this will break not the line, but the particle will have gaps, large gaps. We need to have not zero gaps, but very, very small gaps between the particle in order to have an efficient electrolysis between the leaves like this. Yes, so we pay attention not to make perturbation. So the voltage is low enough not to make realignment. And works of this is the possibility of flows. When you apply an electric field on a liquid, also on water, on an ordinary liquid like water, you make flows. If, of course, the liquid is pure, you cannot see. But if you put a particle in it, you can see that you have hydrodynamic flows. And these hydrodynamic flows are also would be delta perturbations. So we pay attention not to make this.
You expect that when you remove the liquid crystal, the line you form it will remain.
Yes.
You tried this?
As you can see, we make the flow. It's the first operation. During this flow, we take the liquid crystal from one side and we put a new liquid crystal from the other side. We put a pure liquid crystal. And in this way, we remove the liquid crystal which has been charged with these ions. Otherwise, if you measure the resistance, you measure the resistance due to the ions. So we do this.
But if you take completely, you leave in air, for example.
We cannot do this because you see that the wire is not very strong. I estimate that its strength it breaks if the force exceeds 1 nanonewton, which is very, very small. And if I have an interface of the liquid crystal with the air, for instance, this makes a force which is of this order of magnitude maybe larger, and then we risk to break the wire or the model. So I need to make stronger wires to do this. But the first idea is to replace the crystal with an electrolyte to make electroplating, to deposit silver or gold, and to have very good conduction. This is the aim of the life. But we do not succeed. We have many, many steps to do.
More questions?
I have a question. It's more basic. When you minimize have both free energy. And you use Boltzmann entropy. And the omega is V.
The large V is the volume of all which is accessible for the particle. The volume. In the case of the particle on the line, it's the length, large L, and so divided by the volume occupied by the particle, which is just its diameter, 2r. That's why.
Why you get the 2?
Because
then you put out the 3 over 4. 4 over 3 in the bottom.
yes, you are right. I should have dropped this 2. It was joking. Yes, you're right.